This is a walkthrough of Problem 1 on Exam 1 of Module 9 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 1, a 10 centimeter by 5 centimeter rectangular loop of conducting rigid wire is halfway in a square magnetic field region. The magnetic field in this region starts out at 0 and increases at a constant rate of 60 millitesla per second directly out of the plane of the page. Part A, at 2 seconds, what is the direction of the current in the loop? Let's focus on that right now. We got to get how the magnetic field is changing. It starts at 0 and it grows out of the page. Let's put in a magnetic field indicator. So the field is growing out of the page. It's coming right at us at 60 millitesla every second. The loop is fixed. The area of the loop in the field is constant. That doesn't change. At 2 seconds, the field is 120 millitesla out of the page and growing. This loop is going to have an induced current that opposes the change in flux. The flux is growing out of the page. The loop is going to produce a magnetic field that's into the page that opposes the change. We can use the right-hand rule. We can see that the current must be clockwise. We can draw the current in there, and on any of these four sides, we can put our thumb of our right hand along the current. Our fingers are going to curl into the page, inside the loop, for each one of those four directions. You should check this. Put your thumb on your right hand down. Your fingers are going to curl into the page, inside the loop. Now part B, what is the EMF in the loop? So we're getting quantitative. The EMF is the rate of change of the product B times A. The area of the loop that's in the field is 5 centimeters by 5 centimeters. That's 25 square centimeters. That does not change. The rate of change of the field is 60 millitesla every second. And we want to get the rate of change of the product. And we're going to do a little overkill here. We're going to make a table of B times A so we can see how this product is changing. So here's the table. Here's the time, 0, 1, 2, 3 seconds. Here's the B field, starts off at 0, changes by 60 millitesla every second. Here's the area. It's always 25 square centimeters. The area in the field does not change. Here's the product, B times A. We're just multiplying the second column times the third column. If we look at the last column, the product B times A, we can see that the field is changing 1,500 millitesla centimeters squared each second. It goes from 0 to 1,500 to 3,000 to 4,500. So the rate of change of the B field is 1,500 millitesla centimeters squared every second. We can also get it the normal way, the change of magnetic flux. The magnitude of the EMF is d flux dt. And the flux is B times A. The area is constant. We can pull it out. All we need is the rate of change of the magnetic field. And there's the area, which is constant, and there's the rate of change of the magnetic field. And if you multiply these two numbers, you get 1,500 millitesla centimeters squared each second, which agrees with the table. You have to convert the SI unit to get volts, so we convert square centimeters to square meters and millitesla to tesla, and we get 1.5 times 10 to the minus 4 volts, 150 microvolts. Note that the value of the field at 2 seconds is irrelevant. We didn't plug in the 120 millitesla anywhere. The only thing that matters is the rate of change of the field. The EMF at 5 seconds is the same as it is at 2 seconds, because the rate of change of the field is the same, 60 millitesla per second. Part C asks for the force, the direction of the net force on the loop. We should only focus on this horizontal section. There's force on the two side pieces that are in the field, but those forces are going to cancel. All we need is a force on this top section that's in the field. The current is to the right, which means that the electrons are moving to the left. So the velocity is to the left. The magnetic field is out of the page. So we use the right-hand rule. We put our thumb on our right hand to the left. Our fingers are pointing out of the page, and the direction of V cross B is up. But the force is Q V cross B. Q is negative, so the force is downward. That's the answer to part C, downward. Finally, to part D, what direction will the loop have to be moved to reduce the current in the loop to zero? In order for the current in the loop to be zero, there has to be no change in flux. The flux is increasing, so you have to pull it out of the field. And if you pull it out of the field at the right rate, you can get no current in there. The field's growing, but you're pulling it out. So you can make dBA dt 0. So the answer is down, out of the field. That's problem 1.